This lecture is on understanding correlation. So a correlation is an association between scores on two variables. So for example, we might want to look at the correlation between high school grades and college grades, between an employee's motivation and their job performance, or between an employee's job satisfaction and their intentions to quit. So researchers often have hypotheses that variables are related to each other or that one variable might predict another. And a correlation coefficient is a way to come up with a statistic or a number that quantifies the extent of relationship between two variables. So in this lecture, I'm going to review how to graphically describe correlations, review different types of correlations, and then how to calculate a correlation coefficient. So to graph correlations, we create scatter plots. And scatter plots are diagrams or graphs showing the relationship between two variables. The values of one variable are plotted along a horizontal axis, and the values of the other variable are plotted along a vertical axis, and then each score is shown as a dot in this two-dimensional space. So each observation, or in psychology and social behavioral sciences, we can think of each person or each participant will have two values. They'll have a value on an x variable, and they'll have a value on a y variable. So for example, they'll have a value on their SAT score, and they'll have a value on their GPA. Or they'll have a value on their motivation, and they will have a value on their work performance. So each person has two values, and we'll plot those values along an x and a y axis. So here's an example of what a scatter plot looks like. Here we've got two variables. The x variable is the number of exciting activities that are done with a partner, and I assume that this is over, say, like a weekly period. And then the y-axis is marital satisfaction, and we can assume that higher numbers mean more marital satisfaction. So each one of these dots represents a person. And that person was asked to report, say in a questionnaire or a survey, the value on the first variable. Okay, so for example, how many exciting activities do you engage in with your partner on a weekly basis? And then what is your level of marital satisfaction? By convention, we graph the variable that we think of as the predictor variable on the x-axis. So a researcher might have a theory that the more exciting activities you engage in with your husband or wife, your spouse, the more satisfied you will be in your marriage. That is, the exciting activities is the predictor of marital satisfaction. So with that framework in mind, the predictor variable, by convention, is graphed on the horizontal or x-axis, and the outcome variable, or the y variable, is graphed on the vertical axis. Okay? But the main take-home is that each one of these dots represents a person, and you can see that each person has two values, a value on the x variable and a value on the y variable, which can be plotted in this two-dimensional space. And this reveals the shape or the form of the relationship. So what we can kind of see is that these data trend in a positive direction. Okay, so not perfectly, but there's a general trend that the fewer exciting activities, the less marital satisfaction, and the more exciting activities, the more marital satisfaction. So we can start to get a sense of the direction of the relationship between these two variables. And in this case, we say that there's a positive relationship or a positive association between these two variables. So here's the steps for making a scatter plot. you have to draw the axes and then assign the variables to them. And so by axes, we just mean the horizontal axis and the vertical axis. And by convention, the predictor goes on the horizontal and the outcome goes on the vertical. And what is the predictor and what is the outcome will be dictated by some sort of a theory or a research question by a researcher. What you then do is determine the range of values for each variable and mark those on the axes. So just going back to the previous scatter plot, you have to consider what the range of possible values is on each of the variables and then label the axes appropriately. You'll notice that you can have two variables that are measured on two entirely different metrics. That's completely fine, okay? But you just need to determine what is the possible range of values for your x and what is the possible range of values for your y. Okay. And then you're just going to mark a dot for each person's pair of scores by locating where it would land in the two-dimensional space. So here's a simple example. This is from the textbook, but this is looking at the relationship between the number of hours slept the night before and the extent to which people report that they are in a happy mood the next day. So obviously hours slept, that's a straightforward. Happy mood, we can just say that higher numbers mean a more happy mood. So how would we create a scatter plot of these data? Okay, so the first thing is that we're going to create our x and our y axes. Hours slept last night will be our x variable because that is our predictor variable. Okay, you sleep first and then you're in a happy mood. Being in a happy mood the next day doesn't dictate how much you slept the prior night. So hours slept has to come before, and therefore it predicts happy mood. So hours slept would go on the x-axis. Notice that on the x-axis, we've got a possible range of values. Even though our data only went from 5 to 10, we're going to include 0 as the starting place because it is conceivably possible to sleep 0 hours in a night. Okay, and then we could extend the graph beyond 12 hours, but it's unnecessary to do so with the range of values that we have. Happy mood, we would have to know like what are the possible values. So if given a questionnaire and where people were asked, okay, on a scale from 0 to 8, what is your mood? It'd be necessary to know what the range of possible values are. But once we are able to come up with our range of possible values on both our x and our y, what we're going to do is just take each person. So we've got 1, 2, 3, 4, 5, 6. We've got 6 people that answered both questions. How many hours did you sleep the night before? And what is your mood? And we're going to take that person and we're going to plot them in this two-dimensional space. So this person that slept 5 hours had a happy mood of 2. So we just find the intersection of 5 and 2, and that's where we plot that person's point. We do the same thing with the next person. So this person slept 7 hours, happy mood of 4. We're just going to plot their point in the two-dimensional space, and then we do that for all of the other observations. What you see being drawn through these dots is a line of best fit. That's a concept that I will lecture on in a couple more lectures, but right now we can just think of that as a trend line. It's a line that captures the trend of the data. And as we can see that we've got a positive trend here. We have a positive relationship such that in general it appears that the more one sleeps, the happier one's mood, the less one sleeps, the less happy one's mood is. But that's how we create a scatter plot. All right, so there's a couple possibilities for having patterns of correlation. What we'll be mostly concerned with in this class are linear correlations. Okay, so where we expect that the relationship between two variables takes on a straight line pattern. And so having a linear correlation, the relationship can be either positive or negative. So far, we've seen examples of positive correlations, but we'll go over examples of negative correlations as well. It's also possible to have a pattern in which there is no correlation between two variables. So there's no relationship. So I'll review that, and then I'll also review curvilinear correlations as well. So with a linear correlation, the relationship between two variables roughly follows a straight line. And so we could say that based on the pattern that we observed with hours slept last night and happy mood, we would suggest that that is roughly a straight line pattern. This is also an example of a positive correlation. So we can see that the pattern of dots goes up from left to right. And so we can also express a positive correlation as indicating that high scores on one variable tend to go with high scores on the other variable. Similarly, low scores on one variable go with low scores on the other, and middle scores go with middle scores. Okay? So we see a correspondence with high scores on one go with high scores on the other, lower scores on one go with lower scores on the other, and middle scores on one go with middle scores on the other. And when we see that pattern, we've got a positive relationship between the two variables. Alternatively, we could have a negative correlation. Here, our pattern of dots goes down from left to right, and we can express this relationship as saying that high scores on one variable are actually go or are paired with low scores on the other. So what we have here are, let's just say, people's reports of the extent to which they are bored with their relationship, so they're bored with their marriage, and then their marital satisfaction. We see that these two variables are negatively correlated. That is, the more bored, the less marital satisfaction, and the less bored, the more marital satisfaction. So what we have here is high scores on one variable, in this case, high scores with being bored, are associated with lower scores on marital satisfaction. Okay? Alternatively, low scores on being bored are associated with high scores on marital satisfaction. So in this case, high scores on one go with low scores on the other, and of course the middle still go with the middle. So that's a negative correlation. With a zero correlation, or we could say no correlation, there's no systematic relationship between two variables. So here we can't deduce any pattern of highs going with highs, lows going with lows, high on one, low on the other. Basically, those are all possible. So here we've got shoe size and income, and in these data, those two variables appear to be not correlated at all. Why? We have some large shoe size going with high income, but we also have small shoe size going with high income. We've got large shoe size, I'm having a tough time pronouncing that, shoe size with low scores on income, and then lower scores on shoe size, also going with lower scores, and then middle with middle. So no discernible pattern between those two variables, zero correlation. And then we also have an example where we can have a curvilinear correlation. Here we've got a curved pattern of dots. So the relationship between the two variables follows a systematic pattern. There's clearly a relationship here, but it's not a straight line. So one example that is often used in psychology that demonstrates a curvilinear relationship, specifically what is known as an inverted U. Okay, so you can think of this pattern as an upside down U, would be the relationship between physiological arousal. Okay, so the extent to which your heart is beating fast, your blood is flowing, you're, perhaps breathing hard, you're perspiring. Okay, so you're very pumped up. Let's just talk about at the top end, you're very pumped up. At the bottom end, you're not. You're very calm, you're very relaxed, you're in a low state of physiological arousal, and then middle values would be some midpoint. Okay, so what this pattern shows is that the best performance is achieved at a medium or moderate level of physiological arousal. Being too calm, and we can think of this as being, let's just say, cognitive performance, perhaps taking an examination. Okay, so being kind of in a medium state, being alert, being attentive, is good. Being too calm and too relaxed, okay, maybe your brain is not firing, but being too pumped up, okay, your heart is beating, you're perspiring, heavy breathing, okay, that's not good for test taking performance either. So we've got a curvilinear relationship where there's clearly a systematic relationship between the two variables, but it does not follow a straight line pattern. And you can get curvilinear relationships in many different forms. You can get U-shaped relationships. You can get what are called J-shaped relationships, where you might have like a leveling off effect. It suffices to say that there's many different types of curvilinear patterns that we can observe based on whatever the social or psychological phenomenon is, and those are curvilinear correlations. Okay. When it comes to linear, okay, so not curvilinear, but linear correlations, and that's primarily what we will be concerning ourselves with, particularly when we calculate the correlation coefficient, we can express the strength of the linear relationship by calculating a correlation coefficient. And so that's what we'll do in just a little bit, is we'll see how to calculate this number. So we see that a correlation coefficient is abbreviated with this little italicized R. That's our symbol for correlation. And what that correlation ultimately captures is the strength of the association between the two variables. So that is, to what extent with our positive correlation, to what extent do highs really go with highs, lows really go with lows, and middles really go with middles? So the closer this value is to 1, in the case of a positive correlation, the closer we are to a perfect positive correlation. We can think of a straight line relationship where there is an exact one-to-one correspondence, okay, between the lowest value on your x variable corresponds to the lowest value on your y, the second lowest with the second lowest, the highest x value with the highest y value. So we can think of a one-to-one perfect correspondence, perfect relationship. And so that correlation coefficient will depart from 1 to the extent that those dots depart from that perfect straight line relationship. But you can see that with a positive correlation of 0.81, there's a very clear, strong positive relationship. There's strong correspondence. If we move down to panel C, we can see that there's still a positive trend, but the dots are even more departing from that straight line relationship. And then here we've got a correlation of 0.16, where it's even a little bit difficult to pick out that positive trend. Here we kind of get it, but you can see that there's many dots that are departing from that straight line relationship. So this correlation is able to express the strength of the association, that degree of correspondence, with highs going with highs, lows going with lows, and middles going with middles. Well, what about negative? Same principle applies. Is a negative correlation, a perfect negative correlation would be -1. Okay, so a perfect -1, and that would indicate a perfect straight line relationship, all dots falling exactly on a line. And so the different values are just going to indicate the extent to which those dots cluster together in that perfect straight line, or whether they depart from a straight line. Okay, so we've got negative correlations of 0.75, -0.42, and -0.18. So what you can see is that that correlation coefficient gives us two pieces of information. It gives us the direction of the relationship. So positive numbers indicate a positive relationship. Negative numbers indicate a negative relationship. And then the value of the correlation or the size of the correlation indicates the strength of the relationship. So it should be noted that a correlation of 1 or -1 are equally as strong. Those are equivalent, they just differ in the value. Similarly, a correlation of 0.5 is equivalently strong as a correlation of -0.5. They just differ in the direction of the relationship. Here are some guidelines that are given by statisticians in terms of interpreting the strength or the size of the relationship between two variables. A correlation that is around 0.10 would be considered a small or a weak relationship between two variables. A correlation of 0.3 would be considered a medium or a moderate relationship between two variables. And then a correlation of 0.5 would be considered a large or strong relationship between two variables. Okay? And then, of course, you can have values in between. So a value of 0.2 would be considered small to medium. A value of 0.4 would be considered medium to large. So there's a little bit of subjective judgment there, but those are generally the guidelines that we use to describe whether we have a small, medium, or large correlation indicating a small, moderate, or we could say strong relationship between those two variables. So I was just referring to the Pearson correlation coefficient, which we abbreviate as this italicized R, which comes from the creator of the statistic, Pearson. And so a Pearson correlation coefficient is a measure of the degree of linear association between two variables that can range from -1, which would be that perfect negative linear correlation, through 0, which would be no correlation at all, to +1, so a perfect positive correlation. So the correlation coefficient measures the direction of the relationship. Positive number for a positive relationship, negative number for a negative association. It also measures the degree. Okay, so the weakest correlation that you can have is 0. But then as the size or the magnitude increases, the strength of the correlation increases. And again, a +1 is equally as strong as a -1. Okay, those are perfect relationships. The sign is just different. The degree, the direction of the relationship is just different. And importantly, the type of the relationship is linear. So it only works to calculate this Pearson correlation coefficient, or it only makes sense to express a relationship in terms of a Pearson correlation if we can assume that we have a straight line or linear relationship. If we have a curvilinear relationship, we have to use different statistics. Okay, so the assumption here is that the pattern of data is linear. So let's go over the logic. So we're going to calculate a Pearson correlation, but it's important to kind of understand the logic of how it's possible to come up with a single number that reflects the degree of association between two variables. So we can start by asking what the meaning of association is. So for example, if we say that SAT scores are associated with GPA, what does this actually mean about the two variables? And going further, we could say that we think that SAT scores are positively associated with GPA. So when we talk about association, it just means that scores on different variables vary together. They co-vary. Okay? And so what this would mean is that people with high scores on the SAT also have high scores on GPA. People with low scores on X have low scores on Y. Okay? So there's those scores are varying together. They co-vary. Okay. Now we've said that a positive correlation means that high values go with high values, low values go with low values. Highs go with highs, lows go with lows. What is the meaning of high and low? In statistics, we can talk about the meaning of high and low in reference to the mean, okay? So it's all about placement of a score in relation to the mean. So let's just say that the mean SAT score is 500. Scores above the mean are considered high. Okay, simple definition. You have a high score if you're above the mean. Okay, what do we know about that from earlier concepts in the class? If you score above the mean, you will have a positive deviation. Okay, what about low scores? We can just say very simply, scores below the mean are low. Okay, in this case, you can see, for just putting in some numbers to make things more concrete, when you score below the mean, you have a negative deviation. Okay, so high scores, positive deviations; low scores, below the mean, negative deviations. Okay, and we can do the same thing with GPA. Somebody that scores above the mean on GPA is going to deviate positively. Somebody that scores below the mean on GPA is going to deviate negatively. So this should be familiar concepts. But to just be a little bit more precise when we're talking about high versus low, we can quantify in terms of deviation from the mean, really the extent to which a score is high, okay, deviating positively from the mean, and by how much, versus low, deviating negatively from the mean, and by how much. Okay. So our correlation captures that idea of mean deviations. So if we take our x variable and we're just going to plot that along our horizontal axis, and we'll just think of this middle point here being the mean, what we've got on this side would be any x scores that are, say, high scores. They deviate positively in the positive direction. On this side of the x-axis, we've got x scores that deviate negatively. Okay, so having a low score on x will place you on this side. Okay, now we also have our y-axis here. Okay, in our scatter plot, the y-axis was over here, but it helps to put the y-axis in the middle so that we can see the relationship. Okay, so again, each of these scores has a value for both x and y. And so we can say, all right, this score deviates, has a positive deviation on x, but guess what? It also has a positive deviation on y. Okay, so we'll just call this middle point the mean on both. So this particular score and all of the scores in this quadrant are above the mean on x and y. So high scores on both. In this quadrant, we've got low scores on both. And when we say low scores, we're talking about being below the mean on x and y. So we can say that a positive relationship is captured when we have high scores going with high scores, low scores going with low scores, but more precisely, we can say when we see a pattern that we've got people scoring above the mean on x and y, and also scoring below the mean on x and y, we have, and these other scores scoring below the mean on x and y, we've got a positive relationship. What about a negative relationship? Applying the same logic, we have some scores that are above the mean on x but below the mean on y, falling in this quadrant. We also have scores that are below the mean on x but above the mean on y. Okay. So we've got highs paired with lows and lows paired with highs. And more precisely, we can say that high versus low means being above or below the mean. And then when we have zero correlation, we can say that we've got observations falling within all four quadrants. So there's no discernible pattern of data because we've got some scores that are above the mean on x and y, we've got some scores that are below the mean on x and y, we've got some that are below on x and above on y, and we've got others that are above on x and below on y. Okay, so we've got highs go with highs, lows go with lows, but highs also go with lows, so no pattern, zero correlation. Now we can get even more precise, and we can say to what extent are highs paired with highs or to what extent are lows paired with lows. Because what we want to do with our correlation is express just how much the pattern of dots, these pattern of observations, correspond to a perfect straight line relationship. Okay, so with a positive relationship, the best we can do is +1. And that would suggest that the exact amount that a score on X deviates from the mean corresponds to the exact amount that score deviates from the mean of Y. Okay, so more precisely, let's convert our scores into z-scores, because recall that a z-score will express the extent of deviation from the mean in standard deviation units. So regardless of the metric, it doesn't matter that we have SAT and GPA that are measured using two entirely different metrics. It doesn't matter that we would have exciting activities with a partner and marital satisfaction that are on two entirely different metrics. We're going to convert our z-scores, or we're going to convert our raw scores to z-scores, and that allows us to express the extent to which our score deviates from the mean in standard deviation units. So now we're talking about standard deviation units on X and standard deviation units on Y, which are directly comparable. Okay? So we could even say this particular dot right here deviates from the mean of X. Let's call this one SAT. Okay, so their SAT score is one standard deviation above the mean, and their GPA is also one standard deviation above the mean. So you can see that that would fall right along this one-to-one straight line axis, but not all dots do. Okay. So for example, here we've got a deviation of, let's say, 2 standard deviation units, and on X, and I'm just calling this one standard deviation unit on Y. Okay. So what expressing our scores as our raw scores as z-scores is going to allow us to better see the degree of correspondence between our x and our y variable. Okay, with a perfect correspondence when we can say when turned in. I'm failing to have the language here, but when transformed. There it is. When transformed into a z-score on both, we can see the extent to which the score deviates in a similar amount from the mean on both. That is, the z-scores are the same or the z-scores are different. Okay, now I'm going to jump straight to the formula, because kind of with these z-scores in mind, it'll help us understand how this Pearson correlation coefficient works. So the way that we calculate the Pearson correlation coefficient is to take the sum of the z-score, each person's z-score on X times the z-score on Y, and then to divide by N. And so in words, we can say that this is the average cross product of the z-scores of two variables. So we're going to take something known as a cross product, and then we're going to average that. Okay. So what are these cross products about, and why does it make sense that we calculate a correlation coefficient by coming up with the cross products of these two variables? So here's why. Going back to our example, when we've got a score that deviates positively from X and Y on both, okay, and so when transformed into a z-score, we've got a positive z-score on X and a positive z-score on Y. When we take the cross product, which is nothing more than multiplying zx by zy, we notice that we get a positive cross product. Okay. Interestingly, what happens when we take the cross product of a negative z-score with another negative z-score? Multiplying a negative by a negative gives us a positive. So by taking the cross products, that allows us to capture the pattern of data, such when the scores fall in this first quadrant, deviating positively from the mean on both, that is high scores. And when we've got scores that deviate in the negative direction on both, okay, we'll get a positive cross product. So on balance, we have more positive cross products here. We've got a couple that would not give us positive cross products, but on balance, our data, because we have our data points falling in this first quadrant as well as this third quadrant, when we multiply the z-scores together, we're going to get these positive cross products, and therefore when we sum those cross products up, on balance we're going to have more positive, so that will yield a positive number and allow us to express that positive relationship as a positive number. Okay, so again, intuitively, with a positive correlation, we've got highs going with highs, lows going with lows, middles going with middles. But as a way to quantify that, we can see that if we transform into z-scores and then take the cross product, that will yield positive numbers that then when summed together will give us an overall positive number to reflect that positive relationship. Okay. With a negative correlation, it's the same principle. So here we've got scores that are deviating in a positive direction on our x variable, but in the negative direction on our y variable. What happens when we take the cross product? We get a negative cross product because a positive times a negative is a negative. Same thing in this quadrant. Deviating ever so slightly in the negative direction on x, positive direction on y, so above the mean on y. When multiplied together, we're getting a smaller number, but you can still see that it's a negative number. So with a negative correlation, this formula, what this formula is ultimately capturing is on balance, we get more negative cross products, so that when summed together and then ultimately averaged, we're going to get a negative cross product. And then with no relationship, here's what we have. Okay, we've got highs going with highs, positive deviations with positive deviations, positive z-scores with positive z-scores. So we end up with a positive times a positive is a positive when we take the cross products. Same thing here. Negative times a negative is a positive. So we've got some of our cross products are positive. However, we've got the same amount, or roughly the same amount, of cross products that are negative, because we've got scores in this quadrant, which we've got a negative z and a negative y. So when we take a negative times a positive, we get a negative, and then same thing in this quadrant. So on balance, we've got an equal amount of both positive and negative cross products, and those ultimately sum to zero. Okay? So the same formula is going to capture that we've got zero relationship between these variables because we've got a sum of cross products that is going to be equal to zero. All right, so the logic of the correlation is captured very nicely in this table from the book. So what we can see is that when we've got a pair of raw scores, so we haven't transformed them to z-scores yet, but we can just say that we've got scores that are high in x and high in y, low on x, also low on y. We know when we have highs going with highs and lows going with lows, we have a positive correlation. Okay? By high, we just mean above the mean. By low, we mean below the mean. So if you're above the mean, we know that you're going to get a positive z-score because you're deviating positively from the mean, a positive deviation. Okay? Then when transformed into a z-score, we get a positive number. Low scores below the mean, so we're going to get negative z-scores. When we multiply those together, we get the cross product of those z-scores. We'll always get positive z-scores, multiplying a positive by a positive and a negative by a negative. So getting, on balance, these positive cross products will contribute to a positive correlation. So when the preponderance of scores in our data are such that we've got highs paired with highs and lows paired with lows, that will contribute to getting a positive correlation coefficient based on the formula. Similarly, when we've got a negative correlation, we've got highs going with lows, lows going with highs, okay, following the same logic. transform into z-scores, multiply together. On balance, we're going to get negative cross products. So when we sum up those negative cross products, that's going to contribute to a negative correlation. And then when there's not any pattern in the data, we can think of having kind of a middle score on X being paired with any score on Y, okay? So if I'm at the mean on X, I could have a low, middle, or high value on Y, okay? That's expressed here, okay? If I'm at the mean on X, I could have a high, low, or medium value on Y, and same thing. If I'm at the mean on Y, I could have any value on X. So when we've got a z-score that is around 0, and we multiply that 0 by either a positive, a negative, or a 0, we're also going to get a cross product that is 0. So all those zeros ultimately then makes a correlation near 0. So what we can say, and the way this formula works, is that what we'll do is convert each person's score on each variable to a z-score. We'll multiply their z-scores together, since doing so captures the pattern of the data, which hopefully you were able to follow in those previous slides. We're going to average the result. Okay, so we're going to average the cross product of the z-scores across all people in the sample, because we want to say just how strong is that correspondence. To what extent does the extent to which I deviate on X, is that matched with the extent to which I deviate on Y? Okay, so you can see in the formula, we've got a sum and then dividing by n. And you should recognize that anytime we sum something and then divide by n, we're ultimately taking an average. Okay, so a correlation coefficient is nothing more than the average of the cross products between two variables. So let's go through a calculation with numbers. So I've just made up a very simple set of data, and I'm just using X and Y, no real kind of example or context here, but just to keep it super simple. So what we see is we've got X values of 1, 2, 3, and 4, and then Y values of 2, 3, 4, and 5. I've graphed the data points along the X-axis and the Y-axis. What we see here is a perfect positive correlation, don't we? All those points falling on a straight line. And it's a perfect positive correlation because for the amount that we go up in X 1 unit, we're going up 1 unit in Y. So we see this exact 1-to-1. Okay, there's an exact correspondence. Every time I go up 1 unit on X, I go up exactly 1 unit on Y. All right. So if this formula works the way that it's intended to, what's our prediction about this correlation coefficient? It should turn out to be a perfect positive 1, shouldn't it? Okay, based on this logic of capturing the cross products of these z-scores. All right, so let's plug in the numbers. So importantly, we kind of have to remind ourselves, because the correlation coefficient is the average cross products of these z-scores, we have to remember how to calculate z-scores. So z-scores are just each X score minus the mean over the standard deviation of X. So we're capturing that deviation from the mean divided by a standard deviation. Okay. So for Y, again, we're just going to take the deviation of each score from the mean and divide by the standard deviation of Y, and that's how we get our z-scores. Further review, and this is why it's great to be teaching correlation at this point, is that it helps us review many of the concepts that we already had. How do we calculate a standard deviation? Let's remember this formula as well. We're taking the deviations from the mean, we're squaring those deviations from the mean, we're summing, we're dividing by the number of scores, and then we're taking the square root. Okay. So ultimately, a variance is the sum of the square deviations from the mean, and then the standard deviation is the square root of the variance. So we need to calculate the standard deviation of X, and then of course we also need to calculate the standard deviation of Y. So it's a very calculation intensive statistic, but I think it's really valuable to review these concepts and then to be able to see it's not really magic when you see a correlation coefficient reported. It's very kind of logical where that number comes from. Okay, so in doing the calculations, I really like to create these tables or these grids for organizing calculations. We did this with when we calculated variance and standard deviation earlier in the class. So what I've got is the x variable as well as the y variable, and I've created columns to calculate mean deviations, those squared deviations, a column to get the z-score. I've done that for y, and then this final column is going to be calculating those cross products. So here's what we need to do. The very first thing that we need to do any of this is we need to get a standard deviation, right? We need to get a z-score for x. In order to get a z-score for x, we need to get a standard deviation, because to calculate a z-score for x, we take x minus the mean divided by standard deviation. Okay, so that's the first thing we need to do. So how do we calculate standard deviation? We got to take our square deviations, sum our square deviations, get a variance, and then take the square root to get a standard deviation. So this should hopefully all be familiar, but those are the steps. So first thing, we calculate the mean. The mean of 1, 2, 3, and 4 is 2.5. Next thing that we're going to do is calculate deviations from the mean. Okay, so 1 deviates from 2.5 by negative 1.25. So we're going to calculate all of our mean deviations. We're going to square those deviations, and then we're going to take the sum of those squared deviations. So this should, again, be very familiar. This should be a refresher from when we calculated variance and standard deviation by hand much earlier in the course. Okay. Our variance, okay, standard deviation squared, or variance, is our sum of squares divided by n. N is 4 in this case, so 5 divided by 4 is 1.25. And then our standard deviation is just the square root of 1.25. So I got 1.12 by taking the square root of 1.25. How are we going to get our z-scores? Okay, we're going to take x minus the mean divided by standard deviation. So we're going to express the deviation from the mean in standard deviation units. So doing that, we get a z-score of negative 1.34 for 1. Okay, so 1 deviates from the mean of 2.25 by negative 1.25, which when expressed in standard deviation units yields a z-score of negative 1.34. Doing that for all of the data yields the following z-scores. You'll notice that when you, there's some rounding error, those should sum to 0, but a little bit of rounding error, but that's fine, we'll leave it. Okay, I'm going to repeat that exact same process for y. Calculate the mean, get deviations, square deviations, calculate sum of squares, variance, and standard deviation. Okay, so I just repeated that process. Turns out that the standard deviation is exactly the same, which should make sense if you look at the set of data. The kind of average deviation of 1, 2, 3, and 4 from a mean of 2.5 is the same as the average deviation of 2, 3, 4, and 5 from 3.5. All right. So therefore, when we capture the z-scores for y, we get the same z-scores as well. Okay. Next step, we got to get our cross products. So we're going to multiply zx by zy. So what we're going to do for this first line of data is multiply negative 1.34 by negative 1.34. Okay, negative times a negative should yield a positive. The next thing that we're going to do is multiply negative 0.45 by negative 0.45. Negative times a negative will give us a positive, and then repeat that process. Okay, so that's with a little bit of rounding, but I did it to keep the numbers nice. So that's what we get when we calculate our cross products. What is the formula now telling us to do? We need to sum those cross products. When I sum those cross products, we get a perfect 4.0. And then the last thing that we need to do is divide by n. Okay, n is the number of people. Okay, we obviously have 2 scores each, so we've got 8 total observations, but n is the number of people, or number of paired observations, which is 4. Okay, so dividing 4 by 4, we get a correlation of 1.0, which is exactly what we expected. Okay, so as expected, the formula works as intended. So for your homework as well as for the exam, you're going to be asked to go through several calculations where you get some practice using this formula, but hopefully this lecture has illustrated the logic of the correlation the correlation in general, as well as the formula for calculating a correlation coefficient. And I'll be back with another lecture that talks about the statistical significance of a correlation coefficient.